Okay, so, well, in this video, I wanted to explain a little bit about how we can compute other quantities based on the electrical parameters of an induction motor. In a previous video, I tried to explain how we can compute, for example, the power losses of an induction motor, and based on that, compute the output power, but we were considering the currents, the resistance of the equivalent circuit of an induction motor referred to the stator. Now I want to expand a little bit this idea in order to compute in essence the speed and torque curve of an induction motor. In fact, in the right side of this slide, you can observe here that I have placed an image of the typical characteristic curve that relates the speed, the mechanical speed of the motor, that is the rotor speed, and the induced torque. And well, this is basically the behavior that we can expect. And I wanted to mention three important points. First, you can see that we have indicated here what we call the full load torque. What is the full load torque? It is essentially the torque that the motor produces in order to move continuously any load that is placed in the motor. Okay? But notice that we have another type of torque that is called the starting torque. The starting torque basically well, if we analyze this graph, it is indicating that when you start powering the motor, the torque that it will be producing is much higher than the torque that the motor needs in order to move continuously any load. So since the starting torque is greater than the full load torque, we can state that uh, that the starting torque will allow the motor to overcome, okay, or surpass the initial resistance of the motor and start moving any load that is connected to the shaft very smoothly. Okay, that is the meaning, no? Since we have a very high starting torque compared to the full load torque, we can ensure that the motor can move its can surpass its initial resistance and then start moving the object. And well, also, if we go up a little bit, you will find out the maximum point of this curve that is called the pull-out torque, or in other words, it is the maximum torque that the induction motor can produce. And also I wanted to mention that, well, as we stated previously, the sleep of the motor has an influence on the torque we can produce. Okay, so there is a relationship between the rotor speed and also the sleep of the motor that produces certain torque. Okay, so this curve can be computed by considering different values of the sleep of the motor. Okay, so well, what else we can say about this? Well, another point here is that you can see that we have placed here a label for the synchronous speed. So when the mechanical speed is equal to the synchronous speed, we have zero torque, okay? So that is also important to consider, or one important conclusions of this curve, that when the synchronous speed of the motor is equal to its rotor speed, you cannot produce any torque, okay? So that's why it is important to have certain sleep in the motor, because if we have certain sleep of certain difference between the synchronous speed and the rotor speed, well, we can produce different values for the torque. Okay. Now, what happens when you surpass the synchronous speed? No, when the rotor of the induction motor has a greater speed than the synchronous speed. Well, you will enter another region that we call the generator region. Remember that any electric motor can work as an electric motor that is converting electrical energy to mechanical energy, but also we can take mechanical energy and convert that to electrical energy. But that happens for the induction motor when we surpass the synchronous speed. And basically we'll have the following curve. Also, when you start braking, well, you need to produce a negative mechanical power in order to reduce or brake the motor. And this is basically this region in the left. Okay. Now, How can we generate this speed torque curve? Well, we can use the following expression, okay? Here we are, this expression is to compute the induced torque of the motor electrically. But you can notice here that we need other quantities, no? From an electrical point of view. We need the Thevenin voltage, and the Thevenin impedance. That is denoted by this RTH, or the real part of the Thevenin impedance, and this XTH, or the imaginary part of the Thevenin impedance. So we need these two quantities and also the Thevenin voltage in order to, well, compute this value. Also notice that this equation relates not only the electrical parameters with the induced torque, but also we can relate indirectly the speed or the mechanical speed of the motor, because the induced torque also depends on the slip of the motor by this value. Okay, so we can use this expression to relate the slip, and that indirectly considers the mechanical or the rotary speed of the motor with the induced torque. And also, you can observe here at the right that in order to compute the Thevenin voltage, you need to assume that there is an open circuit in this region of the equivalent circuit of the induction motor that is referred to the stator. So at the end, you don't need to consider, or you are assuming that the rotor part is disconnected. And based on this circuit, you can solve this circuit to compute the Thevenin voltage between these two terminals, and you can use the, uh, well, you can turn off the power source in order to compute the Thevenin impedance between these 2 points. Okay. Again, well, we can also derive an equations for the maximum torque. These equations is as follows. Okay, here it is interesting to notice that, well, in the induced torque, we mentioned that, well, we have this expression that depends on the Thevenin equivalent, but also in the resistance R2, and also in the impedance X2. For this maximum torque equation, you can see that the slip and also the value of R2 have disappeared. But it's a little bit simple, the equation, no, in the sense that we have lower terms to consider. And well, you can use this equation to compute this maximum point, no, or this pull-out torque. And also remember that, well, there is a relationship between the torque and the slip, and that also considers the speed, no? But if we want to know at which value of the slip this maximum torque occurs, we need to use the following expression, okay? So basically, that is the idea, no? We have these expressions that can help us to compute these quantities, no? The maximum torque, the induced torque. Also, we can use the curve to estimate the starting torque of the motor and so on, okay? So what I want to make now is to make a brief example of how we can compute this induced torque, this maximum torque, and so on. So for this purpose, we have the following problem. We have that 460 volts, 25 horsepower, 60 hertz, 4-pole star-connected induction motor has the following impedances in ohms per phase, referred to the stator circuit. And well, this is the value of the resistance. And we need to compute what is the maximum torque of this motor and what the speed and the slip it occur. Now we need to compute the speed and also the slip at which this maximum torque occurs. So remember that, well, here we have the curve, and we know that at a certain speed, now I will go to this part, at a certain mechanical speed, we can produce certain torque level. Also, remember that, well, this speed is associated with a certain slip. Okay, so we can compute these quantities. Also, we need to know what is the starting torque. Remember that in order to compute the starting torque, we will notice that the starting torque occurs when the slip is equal to 1. Okay, we will discuss this in a minute in a greater extent. And well, also we want to know what is the rotor when the rotor resistance is doubled, what is the speed and which and at which the maximum torque now occurs, no? So we need to compute again the maximum torque and the speed, but now we are considering that the rotor resistance is double, and what is the new starting torque of the motor. So let's break down little by little. So to solve this problem, just let me annotate in my tablet the values of R1, R2, and so on. So R1 is equal to 0.641 ohms. Also, we know that R2 is equal to 0.3332 ohms. We have X1 that is equal to 1.106 ohms. And also we have X2 that is equal to 0.464 ohms. And we have also XM that is, well, that is the magnetic reactance, that is 26.3 ohms. Okay, so let me close this for now. Well, let me first stop sharing this screen and let me go to my tablet. I will share the screen of my tablet in order to explain these points. Just one moment. And okay, just 1 second, please. Okay, so this is my tablet. Okay, and well, I think that's it. So let me, well, I have draw here the circuit, but remember that one of the equations of the problem was to compute the the maximum torque. So first, what we can do is to draw the circuit that we need to draw in order to compute this maximum torque, and that is this one. Okay, this is the circuit. And here we need to compute the Thevenin voltage between these two terminals and also the Thevenin impedance. So, well, how can we compute this maximum torque? So let me, just 1 second, I need to move some elements here in my computer in order to organize the explanation a little bit better. Just one moment. Okay. So, well, we know that, well, to compute the the maximum torque that the motor can produce, we have the following relationship. We know that the maximum torque is equal to 3 times the Thevenin voltage square, and this is all divided by 2 times the synchronous speed of the motor. This is in radians per second. No, this equation is in radians per second. Also, we need to know the real part of the Thevenin impedance plus the square root of the real part of the Thevenin impedance plus XTH plus X2. And this is a square. And well, this is the maximum torque that we need to take into account. Well, this is the expression. So the first step is to compute the Thevenin impedance based on this circuit, okay? So in order to do that, let me go back to here my tablet, and I will take this circuit, no, this one right here, and I will place the elements, no? Well, here we have the voltage, but the voltage, we know that, well, what we can do first is to assume that the voltage source is off. So I can draw a cable, and then I can write here R1, that is 0.641 ohms. Here we have the value of the inductor, X1, that is 1.106 106 ohms J. Here we have the value of impedance, that it is 26.3 ohms J. And well, we need to compute the Thevenin impedance in this part. Okay. But you can see that it is relatively simple in the sense that well, this circuit is very simple. First, we can add together these two values, okay? And also we can see that the addition of these two values are in parallel with this, okay? So if we add, well, if we simplify this, we can simplify this as follows. We can say that the Thevenin impedance is equal to the addition of these two, well, this resistor and this impedance, that is 0.641 ohms, plus one, sorry, we have 1.106 ohms J that are in parallel with 26.3 J ohms. And this is equal to, if you make these operations, you will notice that the Thevenin impedance is equal to 0.5899 plus 1.075 J ohms. This is the Thevenin impedance. This is the real part, okay? And this is the imaginary part. That is, well, we refer to the real part as RTH, and the imaginary part is XTH. No, that are the values that we need in the expression for the maximum torque. But also we need to compute the Thevenin voltage. So to do that, it's relatively simple. I would draw the circuit again. Remember that we are working with a star connected motor, okay, according to the information of the problem. So the voltage per phase is equal to the line voltage divided by the square root of 3. So we know that the line voltage is 460 volts, and this is divided by the square root of 3. So we can take this value, that is 460 volts, and divide that by the square root of 3. And then we have this resistor, that is 0.041. Also, we have the impedance, that is 1.106 J ohms. And we also have the impedance, no, the magnetic impedance of the motor, that is 26.3 J ohms, okay? And, well, we need to compute the Thevenin voltage, that is the voltage between these two terminals. So the Thevenin voltage is essentially the voltage of this inductor, okay? And, well, the advantage, well, if we say that this is the polarity of the motor, and we say that this is the direction of the current, we can compute the current, and based on this current, we can compute the voltage as follows. First, we can apply the Kirchhoff voltage law. So we have minus the voltage here, that is 406 divided by the square root of 3. And this has a value 0 degrees, plus I times the value of this impedance, not the equivalent impedance of these two elements, that is 0.641 ohms plus 1.106 J ohms, and plus I times 26.3 J ohms, and this is equal to 0. So I is equal to 9.6879 with an angle of minus 88.66 degrees amperes. Okay, now we can compute the Thevenin voltage. that is equal to I times the Thevenin impedance, that is 26.3 J ohms. And this is equal to 254.79 with an angle of 1.339 degrees volts. Okay. And well, this is the Thevenin voltage. We have the Thevenin impedance now. And well, we can substitute these values into the equation that we saw previously. But also, well, I wanted to mention that we need to compute also the synchronous speed in radians per second. So again, we can compute the synchronous speed as, well, we know that the synchronous speed is equal to 125 times the frequency divided by the number of poles of the motor. But we need this value in radians over seconds. So we need to multiply this by 2 pi and divide that by 60 seconds. And well, if we substitute the values that we have, we will obtain the following. We have 120 times the frequency, that is 60 hertz, divided by 4. And you need to multiply this by 2 pi divided by 60. And well, we will obtain the following. That is 188.99 radians over second. Okay. And well, what else we can do? Well, with this information, we can compute the maximum torque if we substitute the values in the equation that we saw at the beginning. So we have 3 times 254.79 square, and this is divided. Now, remember that the equation requires the Thevenin voltage. So my Thevenin voltage was this one. Not, we need to take into account the magnitude. Okay, so that is why I'm using this number. Okay, this is the magnitude of the voltage, and I need to square that. And we need to divide this by 2 times the synchronous speed, that is this value, that is 188.49. Okay, and this is all multiplied by, well, if we go back to the equation, we know that we need the real part of the Thevenin impedance. That was 0.58. So we can write 0.5899 plus, we need to take one square root. Okay, so the square root that we need is this one, no? The square root of the real part of the Thevenin impedance square plus the imaginary part of the Thevenin impedance plus x2, and none of that is a square, and we need to add these two values, and then we need to take the square root of that. So, well, we can substitute those values and we will obtain the following. We'll have 0.5899 square plus 1.075 plus 0.4664 square. And we have these values here. So the maximum torque is equal to 230.8297 newtons. Sorry, I think that my pencil got out of battery, so let me start again. We have 230.82. Oh, sorry, I had a technical problem. Okay. Okay, sorry, 82, 97.4, and these are newtons times meter. So this is the maximum torque, okay? But remember that the problems ask us to compute also at which slip this maximum torque occurs. So remember that we have the following relationship, that for the maximum slip that produces the maximum torque is here, well, before that, I need to write the equation, no, just for clarity. We have R2, sorry, R2 divided by um, RTH. Okay, this is the real part of the Thevenin impedance plus XTH plus X2, and this is a square. So the maximum slip is equal to R2, that is 0.332 divided by the square root of 0.5899 squared plus 1.075, 0.464 ohms. So the maximum slip is 0.20143. Okay, this is the maximum slip. Well, no, sorry. This is the leap at which the maximum torque occurs. Okay, so they are related with each other. Okay, and well, another point that we need to consider was to compute the speed, no, at which this maximum torque occurs. So we have the value of the slip, that is 0.20 2014. And remember that we can compute this slip as the difference between the synchronous and the rotor speed. So this is the synchronous speed minus the rotor speed divided by the synchronous speed. So we know the synchronous speed. Now we can express the synchronous speed as 120 times 60 divided by 4. Okay, that is the number of poles minus the rotor speed divided by 120 times 60 divided by 4. And well, if we substitute for the rotor speed, is equal to 1,437 RPM. Okay, so this is the result, no? Also, we can convert this in radians over second, but well, you can express this in revolutions per minute. Okay, so again, this speed is related to this slip and also is related to this maximum torque. Okay, now another point that the problem was asking us to compute is the starting torque. Okay, how can we compute this starting torque? Well, basically refers to when the motor begins to operate. But we know that when the motor starts to operate, that means that the rotor speed is equal to 0. So we can say that the slip at this point, if we say that the rotor speed is 0, if we compute the slip is equal to the synchronous speed divided by the synchronous speed minus the rotor speed. But since the rotor speed is 0, we can cancel out this. And well, remember that since we're working with a percentage here, we need to multiply this by 100. And well, regardless of that, um, we can say that, well, if you divide this ns by ns, you will obtain 1, okay? 1%, a value of 1%. So This basically states, or this basically means that in the starting torque, the slip should be equal to 1% or should be equal to 1. So we can consider this fact, okay? And well, sorry. I think that I should express this better. This is 100, no? The percentage of a slip should be 100, okay? So what we can do, since the percentage of the slip is 100, that basically means that the slip is equal to 1. So for the starting torque, this means that when the starting torque is related with a slip of 1. So what we need to do in order to compute what is the torque that is produced when the motor is starting, we need to use another formula that was the formula of the induced torque that we saw at the beginning. We know that the induced torque is equal to 3 times the Thevenin voltage. Okay, here we are considering the magnitude times R2 divided by S. And we need to divide all of this by the synchronous speed in radians over second times RTH plus R2 divided by S, and this is all square, plus XTH plus X2, and this is also all square. Okay, just let me 1 second. Okay, this is the expression that you need to use, but we have all the data. Okay, we have that here the slip is equal to 1. Also, here the slip is also 1. And well, also we have all the other values. So it's basically a question of plugging in the values that we know. So this is 3 times the Thevenin voltage, that is just 1 second, 200, okay. So the Thevenin voltage, the magnitude of the Thevenin voltage is 244.79, and this is a square, times 0.332, and this is all divided by 188.49 times, well, times 0.5899 plus 0.33 to a square plus 1.075 plus 0.464 ohms. And well, we can say that the induced torque is equal, well, if we make all these operations, the induced torque, the induced torque, when the slip is equal to 1, that is essentially the starting torque, is 106.58 newtons times meter. Okay, so that is the induced torque, okay, when the motor is starting. So you can see the real challenge here is to compute first the Thevenin voltage and the Thevenin impedance, as we saw previously, and then it's basically a matter of substituting those values into these expressions, no, that we have. But also, I wanted to show you that we can also use this induced torque formula, no, the one that I place here, in order to compute all these quantities and also plot the speed and torque curve of the induction motor that we are analyzing. So to do that, let me go to MATLAB. I have prepared a MATLAB script for this. Let me show you. Let me share my screen. Okay. So here in MATLAB, what I have did is to do the following. I have the following values. I have R1, that is a resistance that was given to me by the problem. This is X1, this is R2, this is X2, this is the magnetic reactance. This is the Thevenin voltage that we have computed previously. This is the real part of the Thevenin resistance, and this is the, well, the imaginary part of the Thevenin resistance. Okay, I am basically writing here the values and assigning each value to a variable. And here, what I am doing is to generate a vector of 15 values in which I am writing different values of sleep that go from 0 to 1. Here, I only changing the value of the first value of the sleep in order to avoid division by 0. Because, well, if you remember some of the formulas, or in particular, the formula of the induced torque is equal to, well, you need to divide R2 by the sleep value. So I am writing a very small value in order to consider or approximate a sleep value of 0. But, well, if you divide by 0, well, you will get a problem there. Okay, so this is basically only a vector that I'm generating to produce different sleep values. In this section, I am writing the value of the frequency of the motor. Here I am writing the number of poles. And with this data, I am computing the synchronous speed and the rotary speed. And also, I am computing the synchronous speed in radians per second. Okay. Now, with this data, I am, well, first I am generating a vector for the induced torque, okay? And I will compute this induced torque using the formula that we saw previously. That is 3 times the Thevenin voltage squared times R2 divided by S. And so I am taking all of the sleep values that I have previously generated to compute this induced torque. Also notice that I am also considering the values that I write here because I need the Thevenin voltage, the Thevenin resistance, and so on. And well, this is all divided by the synchronous speed plus the real part of the Thevenin voltage plus R2 divided by S. And this is all squared plus XTH, that is the imaginary part of the Thevenin impedance, plus X2, and this is all squared also. And well, and I am generating this vector in which I am computing the corresponding induced torque values for the different sleep values that I previously generated. Also, if you remember, one of the equations of the problem was to compute what is happening to the maximum torque when we double the resistance. So what I have did here is to compute the new value of R2 by only taking my previous R2 value, that is 0.332, and multiplied it by 2. And I am applying the same formula, but I am considering the new value of the resistance R2. And again, I am computing a vector or generating a vector that is saving all the values of the induced torque by changing the value of the slip. And in this part, what I'm computing is the maximum torque for the two scenarios. When I am considering the original R2 value and the new R2 value, that is basically the double of the original R2 value. And well, I am plotting the data here of these two vectors. Here, notice that I am writing the, well, as I mentioned previously, I generated a vector for all the possible rotor velocities. And I am generating this plot that relates the rotor with the induced torque for the two cases when I am doubling the value of the R2 resistance and well, with the speed. No, this is the speed and this is the induced torque for R2 times 2. And this is the original one. And here I was showing, or I am plotting the values of the maximum torque and the speed at which they occur. Okay, so let's plot here. all of this. I want you to show you I want to show you the plot. And well, here you can see that the code has generated the plot that we need. You can see that it's very similar to the standard characteristic curve of an induction motor. So in blue, I am showing you the curve of the induced torque that when we consider the original value of R2. And you can see here that, sorry, the maximum torque, okay, that is generated, let me make this smaller, is equal to 230.82, okay? So this basically means that we are obtaining the same value that we obtain by hand, okay? That the maximum point of this speed torque curve occurs at 230.82 newtons per meter. And in the second curve, we have the maximum torque, but when we are doubling the resistance of R2, okay? But you can notice that they occur mostly at the same point, okay? If we analyze this point in detail, you will see that changing the value of R2, well, it changes the curve, but it not changes the maximum torque that the motor is producing. And well, this is expected because if you remember the value, well, the equations for computing the maximum torque does not consider the value of R2, okay? But the curve in general changes, okay? Because well, the induced torque, the induced torque, it depends, that equation depends on the value of R2, okay? And also we can see what is the starting torque, okay? That remember the starting torque is around this position, okay? So let me close this window and let me go down a little bit. And here in this line of code, I am computing the maximum torque, okay? And also getting what is the slip, okay, at which this maximum torque occurs. So you can observe here that we get a value of 0.2. That, well, is very similar to the value that we obtained by hand, okay? And when we double the resistance R2, you can observe that the maximum torque is essentially the same, but the slip has been doubled, okay? So when we double the resistance, the slip also was double, okay? Because we obtain, well, we go from 0.2 to 0.4. Okay, this is the slip at which this maximum torque occurs. And here in this final line of code, what I did was to compute the starting torque, okay, for both cases. This is the torque when R2 was not double, okay, and well, we obtained a starting torque of 106. That is very close to the value that we obtained by hand, okay, and well, as expected, well, the slip should be equal to 1. Well, when we double the resistance, we can see that the induced torque, sorry, the induced torque, that is the starting torque in this case, since the slip is equal to 1, well, has changed. Now we have a greater starting torque, okay, when we double the resistance. So, well, also you can use MATLAB, and also you can analyze the curves that we plot previously in order to obtain these values. Okay, you can use this code as a reference. And in fact, well, if you place your cursor at the beginning of the curve when x equals 0, you can see here that, well, this is associated with a zero speed, a zero rotational speed. We can see that the value of y is the value that we obtain of 106. And for the other curve, we obtain a value of 174. Okay, so there is a correspondence there, no? So, well, I will share with you this code in MATLAB to plot this speed and torque curve. And the only thing that you need to take into account is to change these parameters, but you can use this code as a reference for your homeworks, okay? So I hope I will end this video for now. I hope it was clear and see you next time.